Yeah, I'm doing it, yeah.
Okay. All right.
I was just doing it off my computer screen. Like, you can't see the annotations that you make,
But you can see them on the camera, right?
a little bit. I mean,
Not that well?
Not that well, no.
Oh, really?
Yeah.
Oh, okay. Yeah, I didn't do very much annotation yesterday, so maybe I'll try to do a little bit better job of that today.
Because I mean, it worked really well, I think, last semester when we did from your tablet, but I feel like right now it's like really far away.
Yeah, it's not, actually, I'm not that crazy about this room. Like, there's this thing that kind of like, it's like a barrier between me and the students, I feel like, which is a little bit weird. Well. It's just like tensors.
Right. Must love tensors, right?
They're useful. Actually, this is about as far as we're going to talk about tensors in this class. And that's about it. But for biosolids, trust me, we're going to talk more about tensors.
How are you doing?
Good. Yourself?
Good. Been studying biotransport all day. I have.
I'm so sorry to hear that.
I have. I've read all the notes for the next 2 weeks and been reading through all the textbooks and starting to look at the problems and getting all that stuff figured out. So yeah.
Problems is where the rubber hits the road, right?
That's for sure. Because the theory you can understand it.
Yeah.
But when you have to start practicing it, then it's a whole other ballgame.
That's right. That's how we call it the practice of engineering, right?
Yeah, exactly. All right, well, good luck with the lecture.
Thank you. Okay, folks, before we get started, something super important. Gina, everybody, I think most people met Gina or saw Gina, you yesterday. So Gina is is your plus tutor. And Gina has a question for y'all. So floor is yours, Gina.
Hi, I'm Gina. I just want to get a quick poll of when people want to do these sessions to be. So there'll be, I don't know if you're familiar with Plus, like if you took math here, they had like extra sessions to help you out. And so I was thinking either Monday and Wednesday after this class, since no one will have that time to conflict, or Tuesday and Thursday in the evening around the same time. So if you could just raise your hands for Monday and Wednesday. Okay, and then Tuesday and Thursday. Okay, all right, thank you.
Okay, it looks like it's Monday and Wednesday. Okay. So welcome to the second lecture of biotransport, and we're going to keep going. So just to remind you, last time we talked about those pesky things called units, and I talked about how you kind of have to pay attention to them. And we talked about this GIM, Generate Ideas model, and we'll see more of that going forward. So today, I'm going to start out to talk to you about stress. So what is stress? Anybody know what stress is? Well, stress is when the prof asks you a question in lecture, right? But there's another kind of stress that we care about in biotransport, and it's defined as a force per area, right? So pressure is a kind of stress. Pressure is force per area, right? But there's other kinds of stress besides pressure, and we're going to meet some of them today. Have you all had stress before? Like not the prof ask you question, but you've all, okay. So what are the units of stress? Give me a good system of units. Sir? Pascals, absolutely. How about if we're not using that nice SI system, then we might have PSI, pounds per square inch, pounds force per square inch. Remember we had this weird dynes per square centimeter thing happening, right? That's another unit of stress. Now, stress is something called a tensor, and a tensor is a complicated thing, and we're not going to delve deep into tensors in this class, but I do want you to kind of have just a couple of takeaway ideas from this. if you think about the definition, stress is force per area. Force is a vector, right? Everybody knows that. So that means it has a magnitude and an orientation. But what I want you to get your head around, and this is the hard part, is that area is also a vector. And I know you haven't thought about it that way before, but here's how I want you to think about things. I can define a normal to an area. So let's say that my hand is the area. Then the normal is at 90 degrees to that area. And as I change the orientation of that area, so too does that vector change. And that turns out to matter a lot in stress, because it's not just the direction of the force, but it's also the direction of the area that the force is applied to. So stress actually has two directions in it. And a tensor is a thing that has two directions in it as well. So you all are familiar with scalars. Scalar is something that just has magnitude but no direction. So who could give me an example of a scalar? Sir?
Speed.
Speed. Correct. Right? 40 miles an hour, but you're not saying which direction I'm going in. Any other scalars? Volume. Temperature. Density. Mass. Exactly. Right? How about vectors? Who can give me a vector? Force. Velocity. Acceleration.
I was about to say acceleration.
Sorry, I took your thing. Linear momentum. Angular momentum. Right? Tensor is kind of like the big brother or big sister to a vector. Right? Scalar has no directions. Vector has one direction. Tensor has two directions. Right? How many numbers does it take to represent a scalar? Just one, right? Temperature is 38 degrees C or whatever it is, right? How many numbers in 3 dimensions does it take to represent a vector? Well, it takes 3, right? The x, y, and z coordinates, or x, y, and z magnitudes, or r, theta, z, or whatever it is, right? How many numbers does it take to represent a scalar? It takes 9. So it's 3 times 3. To represent a tensor is 3 times 3. So here's the picture that we have here. We're going to say that stress, and stress gets the symbol sigma here in biotransport. I'm going to have an xx component of stress. I'm going to have an xy, an xz, yx, yy, yz, da-da-da-da-da. 9 components in total. Now, what does that mean? That subscript x is the direction that the force is applied, and y is the direction that the area is oriented, which means the direction that that normal points in. Okay? So right away, we can kind of subdivide this stress tensor into 2 parts. The first part are these guys here. Notice that they have the same subscripts, x, x, y, y, z, z. Those are stresses where the force and the area is in the same direction. And we call those normal stresses. Because the force acts normal to the surface. And then all the other guys so these off-diagonal elements here, those are called shear stresses. And the idea is that the force is not acting normal to the surface, but it's acting tangential to the surface, right? So quick question. When I push down on this desk like this, is that a normal stress or a shear stress? Normal, right? When I slide my hand across the desk like this, normal or shear? It's shear. And whenever you see something about a stress in this course, I want you to ask yourself a question. Is this a normal stress or a shear stress? Because they're different. Usually, in fact, for us, always, shear stresses have something to do with friction. All right? Normal stresses, not so much. Okay, questions about that? You experts on stress now? Stress tensor? Okay, awesome. Okay, what's a fluid? This is always a hard thing to define, right? The usual chain of logic goes like this. A fluid, what's a fluid? A fluid is something that flows, right? What's flow? Oh, it's what a fluid does. Perfect, that was easy, right? It's always good to have a circular definition. It's internally self-consistent, but ultimately unsatisfying. Question, ma'am.
Oh, I was going to answer.
Oh, tell me.
It sustains a rate of deformation.
Sustains a rate of deformation. Explain that a little bit more, please.
Oh, wait. Never mind, sorry.
No, you're real close. You're doing awesome, actually.
Not entirely sure how to.
Okay. Anybody know? I mean, it's kind of up here, right? So inherent in the idea of a fluid is the idea of shear stress. All right? And here's what I want you to think about. And we're going to kind of draw a distinction between solids and fluids here. So anybody have a book? Students don't have books these days. I should have brought a book to class. I'm sorry, I don't have a prop with me here. Thank you. You don't want this back, do you?
I would.
Really? You shouldn't have given it to me. Okay, here's a book. What I'm going to do is I'm going to apply a shear stress to this book. Don't worry, I won't. I won't go full out on it. So how would I do that? I'm going to hold it on the bottom with my hand. I'm going to put my hand on the top, and I'm going to push my top hand in that direction and pull with my bottom hand towards my body. Okay. Now, what does the book do? It deforms a little bit, right? But I'm still pushing on the book. Is it deforming anymore? No. Why is that? Well, there's like some glue here that's kind of holding it all together, right? So this is an example of a solid. It's a material that I can apply a shear stress to, and it deforms a bit, but once it comes to some new equilibrium state, it stops deforming. And that's not a fluid. A fluid does something different. Now, I want you to suppose that this is water, okay? And it's in a pan, because otherwise it's going to run down onto the floor, okay? So I'm holding a pan of water with this hand. Now I take like a little surfboard or something like that. I put it on top of the water, and I push the surfboard to the side. That motion of the surfboard drags the water with it. As long as I keep pushing that surfboard, it keeps moving, and the water keeps moving. So I come back in a week, it's still moving as long as I'm still applying that force. How much deformation is there in the fluid when I do that? Well, depends when I measure it, right? Come back in a week, it's a lot. Come back in 2 weeks, it's even more, right? So the idea behind a fluid is that it is something which continuously deforms, always keeps deforming, so long as I apply a shear stress to it. Notice I didn't say anything about normal stresses. I only said shear stresses. Right? Now there's one other thing. If I wasn't a nice guy, I would take Davis's book. Is that your first name?
Yes, sir.
Yes. I would take Davis's book, and if I was, like I'd had my Weetabix this morning or whatever, I would like keep on pushing and pushing it until what would happen? I would rip the binding, right? And then it would start acting like a fluid, and he'd be sad. Right? So I can make a solid act like a fluid if I put enough force on it. Right? So that's why in this definition of the fluid, we said it's a substance that deforms continuously under the action of a shear stress, no matter how small. So the idea is even if I put a little tiny shear stress on the fluid, it's going to deform and keep deforming as long as I have that shear stress there. Okay? So that's what a fluid is, and I know that's, thank you very much. I know that seems kind of abstract and everything, but we are going to come back and use that later on in the class. Questions about that? Sir, are you good?
I'm good.
Excellent. I'm delighted to hear that. What does your shirt say? Hamburgers made of what? Where'd you get that? A fine emporium. When you see things with little blue stuff on the right-hand side, that means that that's something that I expect you to read, but we're not going to talk about it in class, okay? Because we just kind of don't have enough time to do quite everything in class, and that's pretty simple, so you can read it. Okay, next idea that I want you to think about. So there's these like two famous dudes, Euler and Lagrange, and they were actually pretty smart, and they did a lot of stuff in mechanics, but they had slightly different worldviews. You know, it's like taste great, less filling. I don't know if you've ever seen those ads. Kind of a fundamental dichotomy here. And this relates to two ways of looking at the world and specifically looking at fluid flow. So let me tell you how Lagrange looked at things. The way of looking at things according to Lagrange is called the Lagrangian approach, right? Lagrange said, let's say that I'm standing next to a river, and I want to study the motion of fluid in that river. What I'm going to do is walk along beside the river at the same speed as the water in the river, and I'm going to look over, and I'm going to judge my speed so that every time I look over, I see the same little chunk of water. Could you do that? Yeah, it might be tiring depending on how fast the river's flowing, but it's possible, right? That's what we call the Lagrangian way of looking at things, or the particle following. We're actually following particles along. Right. Euler said, no way, I'm not doing that. What I'm going to do is I'm just going to get out a lawn chair and sit at the side of the river and just look at one place in the river. Now, that's called a space-fixed way of looking at things, because I'm always looking at the same location in space. There's something tricky about the Eulerian way of doing things, which is, you know, I look there and I see some water. I look away, I look back, in the same location. Is it the same water? No, new water's come in and old water's gone out, right? I'm telling you that in fluid mechanics, we use an Eulerian way of looking at things. Sadly, up until now, everything you have done has been Lagrangian. And that Eulerian Lagrangian thing is going to mess you up so bad you can't believe it. Right? It's like your brain is going to catch on fire for the first 3 weeks of this class over Eulerian versus Lagrangian. And you don't believe me now, but you will in about 3 weeks. Okay? Because there's some weird stuff that happens there. Let's just kind of skip to the weird stuff here. Suppose that I have a tube which has a nozzle on the end. All right, so it's fat on one side and thin on the other side. Right? And I am pushing water or something like that through this tube. Right? And I'm going to push the water through steadily. Now, steady in the Eulerian sense means that nothing changes with time. Is that a good definition for steady? Nothing changes with time in the Eulerian sense. So that means that I can look at the water, I look away, I look back, and it looks exactly the same. Same temperature. Same velocity, same acceleration, same everything. That's steady in the Eulerian sense. All right, nothing tricky there, at least doesn't seem like it. Right. Now here's where the weirdness comes in. So I'm going to push this water through this nozzle steadily. Right. So how would I do that? Oh, I don't know. I'd hook it up to the tap and, open the tap and, not change the setting on the tap, and I'd hold the nozzle and the water would shoot out. It's not a real exotic experiment. Okay? Now I'm going to ask you to believe me on this, but just trust me. Basically, the fluid has to go faster at 2 than it does at 1. And the reason is that I have less space to get the same amount of fluid out, and so it has to go faster in that thinner part of the nozzle, right? So the speed at 2 is bigger than the speed at 1. Now, if there's a speed change between 1 and 2, is the particle accelerating? Like a little water particle that's going down that tube? Like if your speed changes, didn't you have to accelerate? So there's acceleration in this flow, right? I'm going slow at 1, fast at 2, so I accelerated. However, this is a steady flow, which means that the velocity does not change with time. Therefore, acceleration does not equal dv dt. I'm really sorry about that. Right? It basically means that you need to unlearn everything that you think you know about mechanics up until this point, because it does not work for Eulerian. Questions?
Can you say that one more time?
You need to unlearn. Sure. So if I'm a fluid particle, at location 1, I'm going slow, right? So let me draw the, the life of a fluid particle here. I start off somewhere over here, right? And I go through the nozzle, and I come out on your right-hand side, right? And what I'm saying is that at cross-section 1, the particle's going slowly, and at cross-section 2, the particle's going faster. So don't ask me magnitudes or anything like that, but if something speeds up, it's had to accelerate, right? So that particle undergoes acceleration. However, I said that this is a steady flow, which means that nothing changes with time in the Eulerian sense. Which means that v is not a function of t. Which means that dv dt is 0. Therefore, a cannot equal dv dt. It's kind of upsetting. Sir?
Acceleration in this case would be a function of the area between.
Yes. So a has dv dt in it, but it has extra stuff. And we'll see what that extra stuff is as we go along. Specifically, in this case, it's v dot grad v, if you want to skip ahead. Yeah. Other questions? So that's kind of weird, right? So another thing I want you to think about is, and actually this is one of the things that biotransport students have a really hard time with, is at the very beginning of every problem, this part of the gym process, you have to make a decision steady, unsteady. It's kind of like a bifurcation point. You go down the steady road or you go down the unsteady road, different techniques, et cetera, et cetera. That steady, unsteady thing, not so simple. Right, Gina? Do you remember that? Yeah. Not so simple to decide if things are unsteady or steady. When you're making that decision, you cannot, illegal, okay, to think Lagrangian. You must think Eulerian when you're deciding steady versus unsteady. Please, 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 okay? In gym, steady, unsteady, decision point, little bell goes off in your head. Ding, 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 think Eulerian. Must think Eulerian. Cannot think Lagrangian. Okay? Do it in that robot voice. It's useful. We'll see how this works in practice in a little bit. Here's a Tegrity lecture. You should check it out. It's awesome. This is about how you calculate the time rate of change of something in an Eulerian representation. So I have the time rate of change of g with respect, or time rate of change of g has the partial of g with respect to time, but then extra stuff. That's the extra stuff that makes acceleration not equal to dv dt, right? What else? Something on streamlines. You should read that too. It's really fun. Okay. Section 2 of the notes. System versus control volume. So I don't think you've had the, anybody know what a control volume is? Ever heard that term before? Sir, have you heard that term before? Control volume? No. Okay. Control volume is a fixed region in space. That's it. Simple. Nothing too complicated there. We abbreviate control volume by CV because it's like way too long to write out control volume all the time. And the surface that encases the control volume is called the control surface, and that has the abbreviation CS for control surface. And we show it always as a dotted line like that, or dashed line. Right? Who chooses the control volume? You do. You are the bosses of the control volume. Don't take any guff from the control volume. Right? The control volume that you choose depends on the problem that you're trying to solve. Right? So I have good news and bad news about control volumes, right? The good news is there is no such thing as a wrong control volume. In the sense that if you choose the wrong control volume for a problem, at the end of it, you will be able to show that 0 equals 0, right? That's not wrong. On the other hand, you kind of already knew that, right? So the bad news is that there are infinitely many stupid control volumes and only a small and finite number of smart ones, right? So part of your job to pass biotransport is to figure out how to choose a smart control volume, right? That's part of gym. Is the control volume concept, is that more Eulerian or Lagrangian? What do you think? You're going to guess Eulerian. Why are you going to guess Eulerian? Oh, I should stand in front of the camera. Sorry. Sorry, Gina. Sorry. Well, no. Yeah, but that's for deciding steady versus unsteady, right? But what's Eulerian? Eulerian is a space-fixed representation, right? I am going to look at one region of space in the Eulerian way, and a control volume is a fixed region of space. So control volumes and Eulerian kind of go together like, you know, PB and jam. Like it's two sides of the same coin. Okay? There's a different way of thinking about things, which is a system, sometimes called a control mass. And that doesn't have anything to do with a region of space. It has to do with a defined collection of matter. So I can, okay, so first of all, who chooses the system? You do. You're the boss. Tell you, a lot of responsibility here. Not only are you the boss of the control volume, you're the boss of the system too, right? That's pretty awesome, right? So I could define the system to be this pen, right? I could define the system to be this leftover plastic bag, whatever I want. Okay. Now, the system could coincide with the control volume, or it might not. And let's do a simple little experiment here. I have a tank with water in it. And this is a valve here, this thing with an X, and that valve is closed. What I'm going to do is define the control volume as shown by that dashed line there. Right. And actually, control volumes, remember, they're 3D, so it's like into the board too, but you know, just this is a cross section. Right. The system is the water that's in that top tank. Is that legal? Am I allowed to do that? Sir, am I allowed? Stop me if I'm doing anything wrong. I don't want to, you know. Yeah, sure, why not, right? You can choose whatever you want. So I'm saying I'm going to choose that dashed line to be the control volume and the water to be the system. Okay? That's just my choice today. So that's at some initial time. Then what I'm going to do is I'm going to open the valve. Guess what happens? Well, you don't have to take fluid mechanics to know that the water runs out of the top tank into that pan at the bottom. Right? So where is the system now? Well, now the system's in this bottom tank, right, or bottom pan here. The control volume hasn't changed or moved, but the system has. Right? What has happened to the mass of the system? Has the mass of the system changed? No. Same water, right? It's just it's in a different place. Right? Is the mass in the control volume changed? Yes. Oh, bad news number 2. Mass is not conserved in an Eulerian representation. Actually, I just lied to you. Mass is conserved, but you don't know how to conserve it. Right? Like, can you really destroy or create mass? No. Well, you can with a nuclear reaction, right? But we usually, the good news is that we don't typically have that in, BME, at least at body temperature and pressure and stuff like that, right? So for our purposes, yeah, mass is conserved, but we don't know how to conserve it in an Eulerian representation, and we are going to use Eulerian representations pretty much all through the year, because that's how you do fluid mechanics, right? So we're going to have to figure out how to conserve mass, and in doing that, we're actually going to figure out how to conserve other stuff too, right? Because if you can conserve mass, you could conserve things like, or balance things like momentum maybe, which is going to turn out to be useful, and energy, and actually you could, conserve whatever you want, but those are the ones that we care about, all right? So I hope that you see that inherent in that little example that I just showed you with the tank and all that, the reason that the mass in the control volume changed was that mass crossed the control surface. Right? Like when I opened that valve, the water drained down and it, crossed that dashed line. If that didn't happen, then mass would have been conserved in the control volume, right? So somehow I need to have a way to represent how things cross surfaces. And I need to do that in math. Because at the end of the day, we're going to want to get to math, right? Because we need that to solve problems, because we're engineers. So the way that we represent how things cross surfaces, or more specifically, how quickly things cross surfaces, is the idea of a flux. And so here's what I'd like you to think about. And there's a integrity lecture on this, but I found this is a really tough concept for students, and it's really important. So I'm going to spend a couple minutes in class to go through this, and then you can watch the integrity lecture if it's not clear. So I want you to think about a little piece of area. So I'm going to say that that area is dA. So I'm trying to draw kind of a little, ellipse in 3D, right? Area of what? I don't know. I don't care for right now. Could be part of the control surface. Could be whatever you want. It's just like some little chunk of area, right? Part of a surface. And I'm going to say that the normal vector to that area is n hat. Right? Now we have the idea that areas have, direction. So I got to take account of that. And I'm going to say further that fluid is crossing that area with velocity v. Right? So I can't do bold, with my pen on the tablet. So whenever I have a vector, I'm going to put a little bar underneath it so you know that it's a vector. Except for normal vectors or unit vectors, I'm going to give them a little hat. So whenever you see a hat or a bar underneath, think vector, okay? And I'm going to ask the question, how quickly is volume crossing that surface? Now that's kind of a weird concept, right? Like you got some fluid going across the surface. That fluid has volume, right? So doesn't that mean that volume is crossing the surface? Yeah, I think so, right? And I asked the question, how quickly does volume cross that little piece of surface? All right. Step one. Suppose that I take that velocity vector and decompose it into two parts. One part is parallel to n hat and the other is perpendicular. So schematically, that looks like this. I'm going to run out of colors here. Am I allowed to do that? Am I allowed to take a vector and break it up into two parts? You betcha, right? Now, the part that's perpendicular to n hat, that doesn't carry any fluid across that area, right? It makes the fluid slide along next to this area, but it doesn't make the fluid cross the area. So if I care about crossing, which I do, then the only part of V that I care about is the part that lines up with n hat. I can chuck out the other part of V. Doesn't matter. Right. How do I get the part of a vector that lines up with another vector? Math. What's the math thing I need to do? Two vectors. I have to take the dot product. Everybody remember that? Dot product. Ma'am, do you remember the dot product? Yeah. Awesome. Do you remember the dot product? Yes. Sir, how about you?
I remember.
Good. Excellent. You okay? Dot product? You remember, right? Yeah. What's the dot product? How do you take the dot product between two vectors? You take the magnitude of the two vectors and you multiply by the cosine of the included angle, right? So it's so dot product of u and v is u magnitude times v magnitude times cosine of theta, right? If theta is 90 degrees, what do you get? What's the cosine of 90? 0, right? So dot product of two vectors that are at 90 degrees to each other is 0, right? So what I'm going to do is say, I only need to work with v dot n hat. That is the speed at which the fluid is crossing the surface. Not the same as the total velocity of the fluid, it's just the crossing part. Okay? So far, so good? All right. Now we're going to do a little thought experiment. Did everybody here brush their teeth this morning? I hope you did. It's part of a good program of dental hygiene, right? Did you floss? No? Your dentist is going to have something to say to you. Okay, I don't want to get too personal here. When you brushed your teeth, what did you do? Well, you had a tube of toothpaste, right? And that tube of toothpaste has a little hole in the end. And you squeeze the tube of toothpaste and the toothpaste comes out in kind of a cylindrical shape, right? I want you to imagine that the little hole at the end of the tube of toothpaste is the area dA. And the fluid that's crossing that surface area dA is the toothpaste. Right? So if I'm only thinking about the component of velocity which is normal to the surface, like this, then it's like I squeeze a cylinder of fluid out through that area dA. And if I knew the volume of that cylinder of fluid, I would know how quickly volume was crossing the area. Right? Now, what is the volume of that cylinder? Well, the volume of a cylinder is the cross-sectional area, that's dA, times the height of the cylinder, right, or the length, I guess you could say it. All right? What's the length of the cylinder? Well, it's the velocity times the time that I'm squeezing the tube. I squeeze for a longer time, I get a longer thing of toothpaste coming out, right? So specifically, if I draw it out, I have something that looks like this. So there's my cylinder of toothpaste or fluid. This area here is dA, and this length here is v dot n hat times dt, where dt is the length of time I waited to have fluid crossing the surface. Obviously, if dt is bigger, then I get a longer L. Which means that the volume of that little tube is just given by this formula here. The amount of volume I'm going to call dV, big V now. That's v dot n dt dA. We good so far? Now, next step. I actually don't care about how much volume is coming out, I care about how quickly. So how do I turn that into a rate statement? I take this dt here, and I put it in the basement on the other side, and that gives me dv dt. It is the rate at which volume is crossing the surface. What would the units of that be? Rate at which volume is crossing the surface. That's weird, isn't it? What is the rate at which volume is crossing? What's a good system of units for that? Meters cubed per second. That is an awesome unit for that, right? Or maybe centimeters cubed per second. Or maybe cubic feet per second. Acre feet per fortnight. Right? Etc., etc. Anything that's volume over time, that's my rate at which volume is crossing. Okay? Now, does that make sense? If dA gets bigger, I'm going to get more volume, right? Yeah, it seems to be good. If V gets bigger, I'm going to get more volume or more rate of volume crossing, right? But remember, it's V dot N. It's not V, it's V dot N. Don't make that mistake. That was so much fun, we should do it again. Because maybe I'd like to know not how quickly volume is crossing, but how quickly mass is crossing. You were thinking that, right? You wanted to know how quickly mass was crossing. I knew you were thinking that. Yeah. How would I get the rate at which mass is crossing from knowing the rate at which volume is crossing? Well, I would have to have some relationship between mass and volume, wouldn't I? If only there was some parameter that was the ratio of mass to volume, then I could just use it. Is there such a parameter? We call it the density, right? So all I have to do is multiply that by rho, and I go from volume crossing per time to mass crossing per time. And that's what we got here. The rate at which mass crosses that surface per time is rho v dot n dA. It's like a cousin to, dV dt. What are the units for d mass crossing or mass crossing per time? Kilograms per second, grams per second, pound mass per fortnight. etc., right? Mass per time. Hey, that was so much fun. Maybe we should just do it for some arbitrary property, because we're actually going to want to do that down the road. So what I'm going to do is say that beta is some parameter which is the amount of B, and I'm not saying what B is, by the way, per mass. Then, without the beta, this is mass crossing per time. And I need to lose, yeah, well, that's in an interval dt. So if I have the dt in the basement, well, let me put it this way. That's mass crossing per time there. If beta is b per mass, if I multiply that by beta, I get b crossing per time. So I can do it for anything I want. Like, I could calculate the rate of ethers crossing the surface per time, right? I would need to know the velocity, the density, and how many ethers there were per mass of the fluid. Whatever you want. Have fun. Okay. Now, next step. That's for a little tiny area dA, which is great and everything. But in real life, usually I want to know what's happening for a whole surface. So that means that I need to add up over all those little dAs. Right? What's the math thing that means add up over small incremental regions? Integrate. Dun, 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 dun. Every biotransport student's favorite word is integrate. And wait for it, it's not just a regular integral. It's an area integral, because I'm integrating over dAs. I'm not integrating over dx's or dy's. It's over dAs. That's special. You're going to like it. Right. Who here knows how to do an area integral? I know. 2. You remember, right, Gina? Yeah. Gina knows. 3, 4. Nobody else? You need to watch the Tegrity video on area integrals, because you need to know how to do area integrals for this class. Okay, that's not optional. Right. So if I do that adding up thing, then I can get the total rate at which volume crosses the surface is written as that. It's the integral. So see that integral sign, and it has a little a underneath it? That means that I'm like adding up over a whole area. That idea of the total volume crossing per time over an area or across an area is so important in fluid mechanics, we give it a special symbol. It's called Q. It's called the volume flow rate, right? Meters cubed per second. Centimeters cubed per second, whatever. Okay. Similarly, for mass, same story. It gets the symbol m dot. That's the mass flow rate. Right? M dot's going to be your close friend for the next 14.5 weeks. Well, plus whatever until the final exam. Then you can forget it all, but you kind of need to remember m dot for the next, 3.5 months or so. Right? You notice that m dot and q are cousins, right? Like they're exactly the same, except you got this rho thing here. So usually you can get m dot from q and vice versa if you know rho. Or, in general, for some arbitrary b, it's that. Rate at which b crosses the surface is the integral over the surface rho beta v dot n dA. Congratulations, you now know how to calculate how quickly something is crossing a surface. Sir. It got into the basement because, remember, we turned it into a rate. Remember I took that dt into the basement on the left-hand side? Yeah. Yeah, I'd hate to have an extra dt floating around. That'd just get in the way, right? Please be careful. There's one thing about this stuff. Okay, so first of all, everybody hates does anybody here like integration? Well, oh, awesome. 1, 2. I love integration. Most people don't, right? Because it's hard. When you have to do one of these integrals, which you will have to do at some point, you need to ask yourself a simple question. What is the a that I'm integrating over? Because we will do problems, like real soon, where it's not so clear what the right a is. So every time you see a q, every time you see an m dot, I want you to ask the question, what is the area? Please, 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 ask that question. What is the area? If you get the wrong area, you're going to get the wrong m dot, right? For sure, then you're sunk. Do not pass go. Do not collect $200. Right? So ask, what is the area? Questions? See you all on Friday. Before we break up, just one thing. Reminder that Friday is a weird thing this week, right? First hour, 3 to 4, upstairs in 2443, if I'm not completely mistaken. Second hour, 4 to 5, flip session in Whitaker. Okay? See you all then.